Hello students, welcome back to the third lecture session on process synchronization. Last lecture we have seen the hardware method of synchronization, using the hardware tools how to do the synchronization. So we saw the mutex locks there and how to acquire the lock, how to release the lock. We also saw two methods that were test and set, and second one was compare and swap. So those methods are used by hardware, by the operating system, but for an application program that was not efficient. That is what we discussed in the last class, and we had stopped our discussion on semaphores. So we had started the discussion on semaphores. So let's review that and then continue our lecture on process synchronization concepts. So we have seen synchronization. We said that synchronization tool provides more sophisticated ways that mutex for the mutex synchronization technique. It's like a mutex lock, and semaphore S is an integer, and we use that with the wait and signal methods. The wait and signal methods were originally called P and V, probane for test, and verogen for the set, the incrementing of the semaphores. So these were the Dutch names, and that's why they have used that P and V of the first letters of those names. And then they were renamed as wait and signal because P and V were not so easy to remember, that P means wait and V means signal. So they thought wait and signal would be more appropriate names, and they gave the names as wait and signal. So definition of wait and signal is given here. So if you see here, the wait method, if here says wait on S, S is a semaphore. So the semaphore variable is an integer variable. So if the wait S is less than or equals to 0. See, I have already explained you in the last class that semaphores can be either binary semaphore or it can be a counting semaphore. So if it's a binary semaphore, then it will be having a value of 0 or 1, and if it is a counting semaphore, it will have a value of any possible valid range that it can take. So here, if it is considered as a binary semaphore, then S value can be 1 or 0. So if it is 1, it means that there is no process that is executing the critical section, and if it is 0, it means that it is that means that some process is in the critical section. So if it is a counting semaphore, then counting semaphore can be any positive number. Supposing we take S is equals to some value n, and then whenever S is positive value, it's not 0, then the semaphore is available, means n number of processes can enter into the critical section. Means we are not talking about actually the critical section. In this case, we are talking about resources and their n instances. So I have given you the example that in your system, you will be having more than USB ports. So if your USB port is a resource, and number of ports that are having on your system are the instances of that resource. So n resources, if S is equals to n, then S less than 0, till S is not less than 0, the instances are available and you can use them. But if S becomes 0, it means that there are no resources, that resources instance are all under usage and they are not available for use. So we have to wait. So if S is less than 0, we are having a busy wait. If S is positive, that means the resources are available and you can decrement, you can use one resource, pick one resource and decrement the available resources by 1. Then what a signal? Signal tells that if that resource is finished, we are finished using the resource and we are releasing the resource, then we have to specify to the operating system that that resource is available. So we increment the semaphore S by 1. So this way we are telling other processes who are waiting for that resource that the resource is available, because this while loop becomes false for that process and it acquires the resource and makes the semaphore minus again. So this way you can use it as a binary semaphore or you can use it as a counting semaphore. So let's understand more details about this. So I said that there is counting semaphore. Counting semaphores is nothing but integer value that can range over an unrestricted domain. So it can range in an unrestricted domain. Next one is binary semaphore. Integer value can range only between 0 and 1. This is same like your mutex log. So 0 means it's not available, 1 means it's available. That can solve various synchronization problems. Semaphores can solve a various set of problems. We will see all of these in a few classical synchronization problems, how this can be used. Next, we here discuss that if there is a statement S1 and S2, if there is two processes P1 and P2 and they are having statements S1 and S2 respectively, and we want that process P2 should not execute S2 until unless P1 doesn't finish executing S1. So let P1 finish executing S1. Till then P2 is waiting for synchronization to happen. Synchronization signal is made. So synchronization signal is made by P1 after S1 gets executed. So when process P1 executes the statement S1, you are saying signal synchronization. Signal synchronized. Synchronization is a semaphore variable here. So it's a binary semaphore. So it's a 0 or a 1. So if it is available, that means it signals. If it is positive, then P2 can execute statement S2. Otherwise, P2 will have to wait until P1 doesn't execute signal. So that is why this is having a wait and this is having a signal. So P1 will tell P2 when to execute S2. It is like that. Semaphores must guarantee that no two processes execute the wait and signal on the same semaphore at the same time. What will happen? Supposing if two processes execute wait and signal simultaneously, two processes execute wait simultaneously, then that's a problem. Why? Because if two processes execute wait simultaneously and another process executes the two processes, there are chances that both will enter the critical section at the same time. So we should take care that wait and signal do not get executed. Wait do not get executed simultaneously by more than one process. Wait and signal should not get executed simultaneously. This especially is very important when you are in multiprocessor system. Because on a multiprocessor system, one process will be executing on one CPU, another process will be executing on another CPU, and hence there will be two processes can execute wait simultaneously, or they can get the signal and that can create a chaos. So thus the implementation becomes a critical section problem where the wait and signal code needs to be placed in the critical section. So to avoid this, we could have a busy waiting in the critical section implementation, but having a busy waiting in the critical section is okay when you are having a short critical section. If your process is going to spend in the critical section only a few minutes or a few seconds or a few minutes, that is fine. But if the critical section is too large and processes execute critical section in hours, then the process who is waiting in that wait, where is a while loop, then that's a problem. So little busy waiting if critical section rarely occupied is fine. Okay. Note that application may spend a lot of time in critical section and therefore it is not a good solution. So because these spend a lot of time in busy in the critical section is sometimes or most of the times it is very lengthy and more processes are continuously executing the critical section. So that's not feasible to have a busy waiting. So with each semaphore there is an associated waiting queue. So what you can do is you can have two operations, block and wake up, instead of putting them into busy waiting by executing a while loop. If the while loop is executing, then it is a spin lock. It's called as a spin lock semaphore. So in that case, the waiting process will simply repeat the while loop and it will be using the CPU just to the process can enter into. To avoid wasting CPU just executing a while loop, is we can have the block and wait operations that will help us more better to execute the semaphores. So what will happen in block and wait? When a process calls a block statement, so if it is in the wait condition, if it has to wait, then in the wait method, it will call the block statement. A block statement will cause this process to have to wait for another process to execute its critical section and finish, execute a signal process. Then the first process can be removed from the CPU and put into a waiting queue. So what happens? That CPU can be allocated to some other process to execute itself. Right? So in this way, we are trying to make better usage or the efficient usage of our resource CPU. So we can have block and wait. So what block and wake up. So block will make the process to be removed from the CPU and put into a waiting queue. So when the other process who finishes execution of its critical section will make a wake up call. The wake up call will make that process to signal the operating system that this has exited the critical section, and any process that is waiting on this semaphore can be removed from the semaphore queue and put into the CPU for execution. So that is what is block and wake up. So each entry in the wake up queue has two data items, value and pointer. For this, we have now used a structure variable, C structure, C programming structure, wherein we have two components, value and pointer. Value is your semaphore variable's value, it's an integer variable, and pointer to the next record contains the pointer to the next process PCB. So if you have 4 processes that are waiting for a particular semaphore, then all those 4 processes will be in the queue, and one process, the first process, will be having a link to the second process PCB. The second process PCB will have a link to the third PCB, and the third PCB will have a link to the fourth PCB. So if another process comes and requests to enter the critical section, then again it will be executing a block statement, and that block statement will make it to go and enter into the queue, and the fourth PCB will connect the link to this new PCB, that is the fifth PCB, fifth process that is going to wait in the queue. So when the process who is there in the critical section executes and exits from the critical section, it makes a wake up call. The first one of those 5 processes that are waiting will be given the CPU for execution. So that is what is the 2 variables of the semaphore. Here there is a definition. This is the type def struct int value struct process star int list and semaphore. So this is a semaphore variable, structure of type semaphore, and it has 2 variables, int value. This value is nothing but the semaphore variable, and this is the PCB's list. This process is going to contain, this list is nothing but a linked list of PCBs who are waiting for the semaphore variable. Now how will the wait and signal be defined? The wait and signal are redefined for block and wake up. So if you see here, there is a block call in your wait method, and there is a wake up call in your signal method. So how this definition has changed now? So wait, initially we had wait, and we had if s is less than 0, then semicolon wait, else we had s minus minus. But now we have, first only we are reducing the value of s value. So the semaphore integer, we are decrementing the value, and then if it is less than 0, if the s value is less than 0, we are saying add this process to the waiting list and make a block call. So it will make a block call. So what happens now? In this case, the semaphore value in the previous signal and wait, we didn't had negative values for semaphore. It would be either 0 or 1, or it would be, if it is a counting semaphore, it would just go and land up at 0, but not negative. But here if you see, s value is decrementing every time a new process comes and asks permission to enter the critical section. So any process who tries to enter the critical section problem, it will call the wait, and in that wait it will decrement the value of s. So in this case, there is no condition that s has to be only maximum 0. But the minimum value that it can take is 0. It can go to a negative value. So this case, it can go into a negative value. Next, what we are doing? If s value is less than 0, we are saying anything less than 0, which means add this process to s list. So this is basically very useful when you are having processes waiting for resource and resource. So in that case, if there are 5 processes who are waiting, then the S value will be minus 5. Because if there are 3 instances, like for example, I'll take again the USB port. USB port, how many ports are there? 3 ports are there, and all 3 ports are already busy. So if another process comes and requests for it, then you will have to wait, or you will have to unplug one of the device and plug this new USB. If there are 4 such processes that are waiting for the USB ports to be free, then what will be the magnitude of, what will be the semaphore value? It will be minus 4. So here, that's what is happening. So if S value is less than 0, then we just add that process to the waiting queue, and we call the block statement. The block statement will remove the process. It will stop the process execution there only, suspends or pauses the execution of that process, puts that in, and then it will get waked up by some other process who calls the signal method. So signal method's wake up call will get one of the waiting process from the waiting queue and puts it into the CPU for execution. So how does the signal method work? So signal method is now signal semaphore star S. First you increment the signal value, the value of the semaphore by 1, and then if value is less than or equals to 0, then remove a process. If it is less than 0, again we are checking if value is less than 0, less than or equal to 0. If it is less than or equal to 0 means, it means that there are some processes that are waiting for the semaphore. Negative value of S value indicates that some processes are waiting on the semaphore. Okay. So if it is less than 0, then remove that process, one of that process from this S list, waiting list. S list indicates waiting processes. So remove one process from there and make a wake up call. Since it was blocked, now it has to be brought back into the CPU. So that process is executed, that process is completed by your wake up call. So wake up call makes a process that is put into the RAM for waiting process is removed and put back into the CPU for execution. So that is what is waited signal. They have changed. Instead of having busy wait, now they are busy executing a while loop on the CPU. They are removed from the CPU and put into the RAM to wait until the process is allowed to enter the critical section. In this situation, deadlock and starvation may occur. How? Deadlock may occur if one of the process is waiting for another process to finish an event or to signal an event which is also in waiting state. So here if you see this example, we have P0 and P1. Now P0 is having a wait on S and wait on Q. P1 has executed wait on Q and wait on S. If you see, they are mutually waiting for each other. Both have gone in a block state. P0 has executed wait on S. S and Q are 2 semaphores now, 2 semaphore variables. Okay, so P0 says I am waiting for the semaphore S, and then it is executing wait for Q. So there is 2 waits, wait for S and wait for Q. Then P1 is waiting for Q and then wait for S. So what is happening? It has asked permission to enter into the critical section for a semaphore S. As soon as semaphore S is available, it will go into the critical section, and after entering into the critical section, it has made a call for Q. It has asked permission to enter Q. But where is Q? Whether Q is free? Q semaphore is busy. Why? Because P has already executed wait on Q. Since P1 has executed wait on Q and Q has the Q is free, it is available for entering into the critical section. P1 has entered the critical section. If P1 has entered into the critical section for the semaphore Q, then it has then requested for S. But P0 has to signal S and P1 has to signal Q. So they both are mutually waiting for each other. So that is why these two processes cannot finish execution at any time, because one of them is holding a resource. It's like P1 is holding one resource and is asking for another resource, which is already been it is already with P1, and P1 will not release that resource because it is asking for a resource that is there with P0. So in this way, since they both are having one resources which the other one requires, and they will not release the resource until unless they don't get this new resource that they are requesting, these two go into a deadlock state. Starvation. A process may never be removed from the semaphore queue in which it is suspended. There may be a process, n processes waiting for a semaphore, and from that n processes, there is, like, for example, if you have a first in, first out, then in that case, all will get the chance to execute and go, because whoever has requested first will get the resource first and it will execute and go. So then whoever makes a new request comes and ends at the end of the queue, and hence it goes on. Supposing you execute this waiting queue as a stack, what will happen? Every new process that makes a request is added to the top of the stack. The processes that are at the bottom will always stop. So this is a simple example, but actually semaphores do not use a waiting queue that is of type stack, because that will always create a problem. The bottom process which is waiting will always wait, because as a new process comes, will be going on executing the critical section, and the one which has requested first may also always go into starvation. But there are other reasons for going into starvation, because there can be a mistake that you can execute wait and wait. Instead of wait and signal, you'll have coded as wait and wait. You'll have coded as signal and wait. First you have signaled and then you are going in wait. So all this will make process to start. Another problem that we have is priority inversion. What is priority inversion now? Supposing we have n processes, and these n processes are going to execute on priority basis. Some process have higher priority, some process have lower priority, and lower priority always has to wait till the higher priority process does not finish its execution. So what will, in this case, if the which is of lower priority has got a critical section, has entered the critical section by getting a semaphore, it has gone into block because there is a higher process. It has been removed from the CPU because a higher process has come into execution. But this higher process is waiting for this lower process to signal. So in that case, what happens? There is a priority inversion. So higher priority is waiting for a lower priority process. Always the lower priority waits for higher priority. But in this case, a higher priority process is waiting for a lower priority because the lower priority has entered the critical section, and that semaphore, the higher priority, is waiting. So in this case, there will be higher priority inversion. So scheduling problem, when lower priority process holds a lock needed by a higher priority process, then we will have priority inversion. So how to solve this problem? The problem we can solve this problem by increasing the priority of the lower process. So whenever such a case comes, you should increase the process who is there in the critical section and who has entered into the critical section and is waiting only to execute for the higher priority process to finish, then you should increase lower priority process by more than one of the current higher priority process. So in that case, this process will become a higher priority process that will finish execution first, and then this process who is actually having a higher priority can finish its execution. So we can priority inheritance protocol can be used to increase the priority. So next is the classical problems of synchronization. Under the classical problems of synchronization, we have three important problems to discuss. First one is the bounded buffer problem. Second one is the reader's writer's problem, and third one is the dining philosopher's problem. The bounded buffer problem, we have already discussed the background of this. The bounded buffer problem is nothing but the producer-consumer problem. In the first class of process synchronization, I have explained producer-consumer problem. So what is this? The producer-consumer problem is that the producer keeps on producing items and the consumer keeps on consuming the items. If they both take the of the products that are there in the market at the same time and manipulate the count by 1, increasing 1 and decreasing by 1, the producer remains the counter by 1, consumer decreases the counter by 1. So if they both manipulate this counter simultaneously, then there will be a of the actual counter at the market by 1. So either it will be 1 more or either it will be 1 less. So next one is reader's writer's problem. Reader's writer's problem is nothing but you have database or you have files, shared files. If you consider data read by multiple people simultaneously, multiple applications simultaneously. But if you want to edit it, if you want to update means to write it or delete some or anything like that, then you should not have anybody reading at that time. So no two writers should write together, no writer and reader should do to write. This data should not this data simultaneously. So that is the reader's writer's problem. Next is the dining philosopher's problem. The dining philosopher's problem talks about philosophers who are continuously thinking and eating. Or they are eating. So there are 5, there's a table with 5 pairs of fork to eat. So it happen that 2 people should not simultaneously, 2 neighbors should not simultaneously pick, it's a case of 2 people picking the forks. This dining philosopher problem is, they have talked about dining philosopher. Actually, in operating systems, we are talking about resources. It is actually resources. In terms of resources, they have talked. We'll understand each of these in details one by one now. How we can solve this using semaphores. The bounded buffer problem. In the bounded buffer problem, there are n buffers. Means n. There's a list wherein we can have n products saved. So it's a buffer, and in each buffer, 1 item. A classroom with n chairs, and in each chair 1 student can sit. Okay. So next, semaphore mutex is initialized to 1. So we have here 3 semaphores. One is mutex, second is full, and third one is empty. You just consider it as your queue. So you all are checking whether the queue is full, whether the queue is empty. If the queue is empty, you cannot delete an element. If the queue is full, then you cannot add the element to the queue, right? So you can just imagine the queue and you can understand this more appropriately. So let's see. Mutex is a semaphore that is used for mutual exclusion. Full is to check whether the buffer is, whether there are items in the buffer, and empty is to check whether there are no empty. The number of empty buffers, empty blocks, and full indicates number of full blocks. So number of chairs that are already occupied, it is indicated by full, and empty indicates how many chairs in the classroom are not occupied. So that is how you can understand this. So this is the structure of your bounded buffer problem. So what we have here? In a do while loop, we have, this is a producer's code. So the producer here is producing an item that is next produced. So he has a variable next produced. In that next produced, he has put his item that he has produced, and then he says wait empty. To wait empty means check whether there is any slot free to accommodate this new item into the buffer. So if it is available, if wait empty semaphore is not in use, then it is available, then he can get that. If it is, if buffer is empty, then he will come to mutual exclusion. He will wait for mutual exclusion. Means what? It should wait till the buffer, till the mutex empty is there. Because if the consumer is consuming, he will reduce the, he will update that empty block, right? Because one of the buffer will become empty when the item is consumed. The box will become empty when that box item is consumed. So that is why you should wait for empty. Then wait mutex. Wait mutex is mutual exclusion. It's for mutual exclusion. Only one process should be entering into this thing to add the element to the buffer. So manipulating the buffer is done in mutual exclusion. So wait for mutual exclusion. If that other process is not there in manipulating the buffer, in picking the item from the buffer, then the producer can go and enter an item into the buffer. After it finishes entering the item into the buffer, it can signal mutex. Means what? It can tell the consumer that the buffer manipulation is over and you can go and manipulate the buffer. You can pick the item that I have put into the buffer. So that is what it signals. It signals to the consumer that the item is put into the buffer, you can consume it. Next, signal full. What does signal full do? Just now it has added an element into the buffer. So it manipulates the full value. So one of the box is occupied now. So it has to say if there were 5 products already in the buffer, 6th product is added. So it has to be manipulated. So we are saying the signal full. Now full will become 6 because 5 were already present. New one is added now. So signal full is now 6. So that is how the producer works. So can you all think of what will be the code for the consumer? Just try the code for the consumer. Seeing this, what do you all think? What should be the first wait? What should be the next wait? What should be the signal? What should be the signal here? What will consumer wait for? Consumer will always wait to see if that buffer is having some item or no, right? So consumer will wait for full first. It will wait for full, then it will wait for mutual exclusion. Then after consuming the product from the buffer, it will signal mutual exclusion and it will signal what? Empty. Why? Because it has consumed an item. So it will signal empty. So just see the consumer code now. Is that right? So it will first wait for the buffer to become full. If it is full, if there are some products in the buffer, then it will wait for mutual exclusion, so that if producer is manipulating the buffer, if it is adding the product to the buffer, then it should wait till that producer finishes its manipulation. Then once producer finishes, then consumer will enter into the buffer to consume the next consumed. So it will get the item to the next consumed from the buffer, and then it will signal mutex that I have finished consuming the product. Then it will signal that the buffer has become empty. One buffer has become empty. From n buffer, one buffer I have consumed one product. So one buffer has become empty and it will continue to work on, it will go in for consuming that product. So first, in the producer is producing, then it will wait for empty, then it will wait for mutex semaphore, then it will add the element to the buffer, then it will signal mutex, and next it will signal full, and then it will continue with execution. Here it will first wait for full. When it is full, it will wait for mutual exclusion, then it will consume the product, then signal mutual exclusion, mutex, then signal empty. Next is the reader's writer's problem. So as I said, reader's writer's problem is when you are having files or when you are having data, number of people can read and one writer or two writers together cannot manipulate this data. So n readers can read simultaneously. There is no change in data. If one person is reading, second person is reading, third person is reading, or n persons are reading, data is going to remain the same. But if this is a writer who is writing, then what happens? And one reader also, then the reader will not get the right data because the writer is manipulating the data. So you should always keep in mind that only one writer should be allowed to write. N readers can be reading together, but one reader and one writer together cannot do it, cannot manipulate the data, cannot access the data simultaneously, and two writers also cannot access the data. So more than one writer cannot access, one writer and any number of not allowed, but only any number of readers and no writers is allowed. So that is what is the readers writers process. So a data set is shared among n number of concurrent processes. Readers only read the data set, they do not perform any updates. Updates here means deletion, addition or changing the values. Writers can both read and write. Okay. The problem here is allow multiple readers to read at the same time. Only one single writer can access the shared data at the same time. Several variations of readers writers problems are considered. We will see them, what are their variations and how we can do that. But how to implement this? To implement this, we have a data set and we have some semaphores and we have an integer variable. So we have two semaphores here, read, write, mutual exclusion. N number of readers can read together, but reader and writer cannot do together, writer and writer cannot do together. So for that we have read, write, mutual exclusion. Next we have semaphore mutex. Semaphore mutex is used to mutual exclusion on read count, so that we don't, n number of readers will be reading the data. So in that case we will be counting how many people are reading the data. So what we are doing here is, there is a data set. If there is first person who comes and says I want to read the data set, we will make a count. Second person enters and says he wants to read the data, we will increment the reader to 2. So every process who is entering to read, that process is incrementing the read count. And when it finishes reading and exits from the reading, it will decrease. So this read count processes manipulate together will be wrong. We need to have a semaphore or a semaphore that will take care that this read count is not manipulated simultaneously by n processes, 2 or more processes. So only one process should execute or modify this read count. So that is why we are having a mutex semaphore. So let's see the code now, how it works. So this is the writer's code, the writer's process. So if you see, we are saying wait for read, write, mutex. Since here read count is not there, so we are not using the normal mutex. We are only using a read, write, mutex. So only reader, writer, mutual exclusion mutex semaphore is used. So wait for read, write, mutex. If there is nobody who is writing or nobody reading, then you go and manipulate your writing. Go and do your writing process. After you finish the writing process, you signal the read, write, mutex. So if anybody else, any other process is waiting for reading or for writing, only either the writer can enter or n number of readers can enter. So we have to wait for that signal. This is the reader's process. So how is the reader's process? You will go through this and try to understand what is happening here. So we have the write mutex, then we have the read count incrementation, then we are checking if there is single reader, if it is a first reader. If it is a first reader, then we are checking for mutual exclusion of reader writer, then we are signaling mutex, then reading process. What do you all think? What is happening here? Are you all able to figure out what is happening? So it's simple. First we will wait for a mutual exclusion on the read count. So to manipulate read count, we need to wait for the mutual exclusion mutex. We have to wait for the semaphore mutex. When the mutex is allowed to access, then we will go and increment the read count. So if two process says that I have to read the data set, then one of them should have go and So that is what is happening here. So wait on mutex. After wait on mutex, read count is incremented by 1. So here we are incrementing the read count by 1. After it finishes read count by 1, check how many readers are there. If there are no readers and this is the first process who is reading, then there is a possibility that writer is manipulating that data set. So we should see whether we have to wait for read-write mutex, so that there is mutual exclusion between readers and writers. So wait for the read-write mutex. Then if the read-write mutex is available, so here we are waiting for the read-write mutex. If the read-write mutex is available, then you will signal the mutex. Signaling the mutex will allow the other process who wants to read the data set to increment the read count and enter into the reading process. So then after this process gets signals mutex, it will start reading. So once it finishes reading, then it will wait for the mutex. If somebody else is manipulating the read count by incrementing or decrementing, it has to check for both, whether somebody is reading or incrementing the reader count or decrementing the reader count. So wait for mutual exclusion. If it is available, then decrement the read count. So this process finished reading, so it will decrement the read count. So if read count is equals to 0, that means no readers are present. This is the last reader. Then in that case, you will signal the read-write mutex. So that other process, if any process is waiting to enter to write the data set, then it will write the data set. Once that is done, it will signal the mutex. Signaling the mutex, other process who wants to decrement the read count, increment the read count, or if there is this thing available or no, based on that, it will cut. So that is the reader-writer problem. So the variations in reader-writer problem is reader first reader and writer problem. The first variation is first reader and writer. The first reader-writer means, first reader means what? Always the reader is given the first preference to enter. If the writer requests and the reader also requests, simultaneously the reader is given an option to enter the critical section. So in this way, what we are doing, supposing now there is some readers who are already reading, a writer comes and says, I want to write. Critical section, it is not allowed, the writer is not allowed because there are some readers reading the data set. The writer goes into wait mode. It calls a block statement and goes into the wait mode, goes into the waiting list. Now, another process comes in and it says it wants to read. Now, writer is waiting. There are some processes that are already reading the data set. And another process enters into the system and says it wants to read the data set. The policy is first read, right? So process is saying that it wants to read. Writer is made to wait and this process is allowed to read. So as many number of processes come and say they want to read the data set, even as to it is made to wait and allow the readers are allowed to read. So, read writer. Is second reader writer version. Second reader writer. That means the second reader writer is given the first preference and reader is given the second preference. If readers are writing, one writer who is interested to, once the writer says that it wants to write into the data set, any number of readers that come in, they will be made to wait only when writer finishes writing as soon as it's possible. Then only the readers who came after the writer to read the data are allowed to read. Only when writer finishes, the reader is allowed to read. So that is second reader. So first reader means reader is given the first preference, writer is given the second preference. Second reader means writer is given first preference and reader is given second preference. So that is what it is. First variation is no reader kept waiting unless writer has permission to use shared object. Right? Reader is not made to wait. As soon as it comes, it is allowed to read because writer is made to wait. Second version, once writer is ready, it performs write as soon as possible. any reader who wants to read the data set has to wait till the writer finishes the write. Both may cause starvation. Why? Because, see, in the first variation, first reader, reader is given the first preference and writer is given the second preference. See, writer makes a request that it wants to fetch the data. Reader is coming on, one after the other, readers are reading the data. And readers are having first preference. If the readers keep coming simultaneously, and in the second case, the readers can go on coming and readers will be in waiting state because writers are having the higher preference, and hence a balancing between them and a solution to have such that neither the reader starves nor the writer starves. So these solutions are there, but it is out of the syllabus. Problem is solved on some systems by kernel providing reader-writer locks. So one by solution is, a simplest solution is provide an operating system lock for the reader-writers. So only when the lock is acquired by the reader or writer, whoever acquires the lock will be able to read and write. So that is one solution. Next is the dining philosopher's problem. So in the dining philosopher's problem, I told you that there are 5 philosophers who are sitting around the chair and there are 5 pairs of chopsticks that are kept. So here the problem is that the 2 neighbors are going to use the same chopstick. So this is a general discussion, but it is basically regarding resources. A resource can be shared among any processes. That is what is the idea. So how you are going to make this? So if the process has already acquired one resource and is trying to acquire another resource, but this resource is available with somebody else and it is waiting for some other resource. So in this way, if there are processes that are waiting for other resource that is held by another process, there will be a deadlock. So that is what is dining philosopher's problem. So here philosophers spend their life alternating thinking and eating. So don't interact with their neighbors. Occasionally try to pick up 2 chopsticks, one at a time, and try to eat from the bowl. So they need to eat need both the chopsticks to eat, then release both of them when they are done. So in this case, 5 philosophers are there, and we have this shared data. We have a bowl of rice, that is a data set, and we have semaphore's chopstick of 5. Since there are 5 chopsticks, we have taken them as an array of 5, and all of them are initialized to 1. So initialized to 1 indicates that they are available. Initialized to 0 indicates that if they are set to 0, it means they are not available. So here, this is the ith philosopher's structure. So while, in the do while, wait for chopstick of I, wait chopstick of I plus 1 mod 5, and then you have the eat, signal chopstick of I, then we have signal chopstick of I plus 1 mod 5, and then 3. So how this is going to work? Since you have already learned reader-writer's problem, I think you all will be able to now guess what is happening. I is the left hand chopstick, and chopstick of I plus 1 mod 5 is your right hand chopstick. So it should get both the chopsticks to eat. So that is why it should wait for chopstick of I and chopstick of I plus 1 mod 5. If both chopsticks are available, then only it will eat. After it has got both the chopsticks, then only it will signal for chopstick of I and chopstick of I plus 1 mod 5. So you can just work it out and see. So take I value as 1 and then see chopstick of 1. So the first philosopher's left hand will be the first chopstick, and 1 plus I plus 1. I is 1 now. 1 plus 1 is 2. 2 mod 5 is 2. So second chopstick is a right hand chopstick. So first chopstick is left hand chopstick and second chopstick is the right hand chopstick. If both are available, he will pick. So if this is available, he'll pick one. Then when this is available, he'll pick one, this one, and then eat. Then leave the chopsticks and then start thinking. So first he will leave the left hand chopstick, then he will leave the right hand chopstick and start thinking. So what is the problem here? Do you all think that there is any problem in this algorithm? Yes. If all 5 of them pick up their left chopstick before they pick up the right chopstick, then what happens? All the chopsticks are in use because all left hand chopsticks are picked. If I pick my left hand, my neighbor has picked my right hand chopstick. His neighbor has picked his right hand chopstick. So in this way, we all are having only one chopstick. The other chopstick is not available to eat. So all of them go into wait infinitely. So there can be starvation. So here, if 2 people try to pick up the common chopstick between them, then there is an issue. So how to solve this problem? So to handle the deadlock situation in this case, such case, allow at most 4 philosophers to be sitting simultaneously to eat. Allow only 4 people to sit on the table. Don't allow 5th person only 4 philosophers. No 5th philosopher. Right? So what happens? At least one person will get both the chopsticks and he will eat, and hence when he finishes, the others will get. So it will not be a deadlock situation. They will have to go into a wait, but they will get the chopstick. Second option. Allow a philosopher to pick up the fork only if both are available. Only if both are available, allow him to pick up the chopstick. He will not pick up the chopstick and keep it in his hold for the other chopsticks to be available. So if both are available, he will use it. Otherwise, he will not pick up both the chopsticks. He will keep the chopsticks until unless both are not available. Next one is use an asymmetric solution. An odd numbered philosopher picks up first the left chopstick and then the right chopstick. So odd philosopher will take the left chopstick. So first one will pick the left chopstick and then he will pick up the right chopstick. But the even number of philosophers should pick up the right chopstick first and then the left. So what happens? If I am an odd person, then I will pick the left chopstick. My neighbor on the left will be an even numbered philosopher. See, he has to pick up his right chopstick first. So we both will be fighting to pick up the chopstick. So whoever gets the chopstick first will be able to eat. So again, the issue. So what are the problems with semaphores? The problems with semaphores can be coding problems. So you can code signal and mutex. Actually what happens? Signal and wait. So you may first signal and enter the critical section and then execute the wait. So at the finish of the critical section, at the exit of the critical section, you will execute wait. So actually first you should wait and then you should signal. But you are doing what? You are signaling and then you are waiting. So in this case, two or more processes can enter the critical section simultaneously. So that's an issue. It can have wait and wait. Instead of writing signal at the end, you will have written wait, coding problem. Okay? So wait and wait. So that's an issue. You are waiting first and after the execution of the critical section, again you are waiting. You don't want to enter the critical section, you want to enter remainder section and you are executing wait. You are making a block statement. You only have to signal. So you have already put some processes into block and you now block yourself also. Who is going to make a signal? Actually you require to make a signal that I am exiting the critical section and whoever is in wait has to get up and execute. But since instead of you making a signal, waking up somebody else, you also go to sleep. Everybody will go to sleep. So that's an issue. So deadlock and starvations are possible. Omitting a wait or a signal can also, or both, can also cause a problem. So all these are the things that you need to take care when you are using such critical section problem solution, that is semaphore problem. Next one is monitors. We have seen so many solutions wherein there were already trying to solve a critical section problem and The solution itself was creating a critical, was going into executing the wait and signal. Two processes can execute the wait simultaneously, right? So all these can be solved using a concept called as monitor. A monitor is a high-level abstraction that provides convenient and effective mechanism for process synchronization. So it's another level. So we have critical section solution, problem solution, and on that we have the monitor. So it is an abstract data type, an internal variable only accessible by code within the procedure. So it's only accessible by the code within the procedure. So only one process may be active within the monitor at a time. So if you create a monitor for this critical section problem, then only one process can be within the monitor, not n processes cannot be there in the monitor. So, but not powerful enough to model some synchronization techniques. So it's not so very powerful to execute all the critical section problems. So what you can do is you can combine two critical section problems. So like you can have monitors and semaphores together, right? So that way you can try and get it more better solution. So here you have the structure of a monitor. A monitor can be created of type monitor. Okay. Shared variable declarations are done first, and then you have procedures. So you have n procedures and you have an initialization code. So these procedures are, if any process who wants to execute them, the process, then only one process can be there present in this monitor. Two processes cannot execute two procedures here. Only one procedure they can execute. So one process, once starts executing a procedure, the other processes have to wait till this process finishes this procedure execution. This is a structure or a semantic view of your monitor. So you have shared data, you have operations, you have the initialization code, and that is the entry queue. The processes who are waiting for to enter into the critical section. So the first box over there, blue color, indicates the first process that is waiting, and the first process will be having a link to the next waiting process. This will have a link to the next waiting process. This will have the link to the next process, and the null indicates here that this is the end of the list. So when this process enters into the monitor, the first process that will be waiting will be the second process. So these will be the waiting process. Monitors can have conditions, like here you can have two conditions. It's not necessary that you have two conditions, but you can have n conditions. And these conditions will have two operations, wait and signal. So as we have seen the wait and signal in semaphores and all that, it's the same wait and signal. So a process that invokes the operation is suspended until x.signal is called. So on this x also you have wait and signal, y also you have wait and signal. Any process who wants to enter the monitor will have to wait for any of these conditions. So if x.wait, x is busy, then another process can go for y. If y is free, it can take the y condition and it can execute. So in that way, it can have two conditions. So here there is how your conditional monitor can execute. So we have the entry queue there. We have this monitor as we have seen in the previous example. We have x and y there. So you can see there is a queue for x and y also. So any process that is waiting for x is queued for x, and as x any of the process does x.signal, then from that queue one next process is put into the monitor for execution. Similarly y. So in this case x and y have to be two different types or groups of processes. They cannot be of the same group. So conditional variable choices.